My name is Yash, and today we're going to be doing Topic 1 Planet Earth for the GCSE Edexcel Astronomy course. So we're just going to cover the main topics and what you have to do in each of them. So the first thing we have to learn about is the shape of the Earth. Now, I know we're told all throughout school that obviously Earth is a sphere, Earth is a ball, but it's actually not exactly true. Earth has a shape what we call an oblate spheroid. Now, what that means is Earth is it's essentially like uh, almost a ball, but it's a little bit squished. And the same goes with any other type of spinning object or anything. So the moon, the sun, they all spin, so they're all called oblate spheroids. This is because of what we call centrifugal force. So basically, as it spins, there's a force created that sort of flattens it out a little bit. If you imagine like kind of like a Beyblade when you spin it and it appears to flatten a little bit. So yeah, that spinning force creates a bulging in the center, which flattens it out, and it basically just looks like a square sphere. So I've got an image here. Yeah, if you just imagine like instead of a perfect sphere, it kind of compresses a little bit. And I know that word centrifugal force sounds a bit confusing, but all it is just the opposite force to the spinning force, which creates that compression. So you can see this diagram here, which shows that. It's just the pulling force outwards opposing to weight. So actually, if you do some research and look at it, centrifugal force doesn't actually technically exist, but it's like Newton's third law, where you just get an opposite reaction where it like opposes the spinning force, which is why it bulges a little bit. But a lot of the time, this bulge is like really barely noticeable. And in order to have a scale of, you know, how unlike a sphere it is, how bulged it is, we have this thing called eccentricity. Now, I basically already said it, but eccentricity is what we use to scale how unlike a sphere an object or an orbit is. It sounds a bit strange, but you'll see what I mean. So yeah, as you can see here, the more eccentric an object is or its orbit, the more it deviates from the circle. So if you've got a perfect circle, like obviously you wouldn't get one in real life, but if you could somewhere find a perfect circle, its eccentricity would be zero. And then as you get closer to like an oval or almost like a line, the eccentricity would increase. So if you just got no eccentricity, it's a circle, and then high eccentricity, it's a lot more bulged. So for most objects and most orbits, the eccentricity is like really close to zero. So you can't actually tell that hard. So when you're thinking about Earth's orbit and things, you do have to say it's elliptical, it's not spherical. But when we're doing calculations and things, we can assume it is because the answers it gives us are very similar. Okay, so the next part of this topic is just some basic informations about the solar system, planets, and things like that. So first we have to cover diameters of objects. It's a bit, it's a bit of useless information that I'm telling you because you get it on your formula sheet anyway, but it's just good for you to know and understand. So the Earth has a diameter of 13,000 kilometers. The Moon has a diameter of 3,500 kilometers. And what's important to notice here is that Earth has a diameter that's almost four times as much as the Moon. That's an important fact to remember because it comes in later when you talk about how back in like the old days in BC they used to use like try and figure out the ratio between the Moon and the Earth to figure out the Moon's size. And then another important fact is the distance between Earth and the Moon. Like I said, all of this is on the formula sheet. It's just good for you to understand. The next is like the parts of the Earth. I'm sure you guys have already probably done this before because you do this in year seven and eight in science and everything. But obviously, just to remind you, obviously you got inner core on the very inside, then outer core, then mantle, and then crust on the very outside. And you got all these like little pieces of information. These aren't as necessary, but they're just here in case you want to know. All right, so the next part is a little bit more important because it comes to use in a lot more further topics such as topic six, topic three, all the other ones. It's about latitude and longitude. Lots of you guys may already know about these systems and how they work, but it's just good to go over to make sure you know the facts. So for now, latitude, it tells us how south or north something is, ranges from minus 90 degrees to plus 90 degrees, or you can put for minus 90, you put 90 degrees south, and then for plus 90, you could put 90 degrees north. Doesn't really matter. Zero latitude is the equator. That's an important fact to remember so you can tell like where you're coming from, where you're going. Um, and then a couple of important things you need to know as well is important like lines of latitude on the Earth. So the North Pole is obviously right at the top, so 90 degrees north. The Arctic Circle, the two circles you can see 66.5 degrees north and 66.5 degrees south. They take the points at which above that on certain solstices, certain days, the sun will stay above the horizon. So, so for instance, when it's the summer solstice, like 22nd, 23rd of June, above 66.5 degrees north, the sun won't set for the whole day. And the same is true on the winter solstice around 22nd, 23rd December. When you go below 66.5 degrees south or minus 66.5 degrees, then the sun won't set at all. You don't really need to know that for now. It's just why it's there. And then the Tropic of Cancer and the Tropic of Capricorn. So again, it's to do with the solstices. Um, on the summer solstice, if you're on the Tropic of Cancer, the sun will be directly above you at noon. So what that means is it's passing directly overhead. And the same is for the same is said for the Tropic of Capricorn on the winter solstice. Right now, just for this topic, you just need to know what these like where these lines are on the Earth, and you don't need to know what they're for. But in later topics, you'll have to learn how to use them for to know things. The next component of latitude and longitude is obviously longitude. So longitude measures how west or east you are. It ranges from 180 degrees west to 180 degrees east. Do you think it like because obviously this is it's a globe, right? So oh sorry, oblate spheroid. So it goes all the way around like a circle, and where it starts, so 0 degrees on longitude is the prime meridian, which is Greenwich. So it's around like it goes right through London because that's near like the center of our map if you see. And so I've got this diagram here to show that. So you've got the prime meridian at 0 degrees, and then you see you've got 30 degrees, 60 degrees, 90 degrees either side, and that will go all the way around obviously to the back of the earth. An important thing to notice is this is what we use for time zones, right? Longitude. So how far east or west you are dictates which time zone you're in. So every like 1 degree you go on longitude means a difference in 4 minutes in your local time zone. So let's say I'm in London, right? I'm right on the prime meridian. That's 0 degrees for me. So I'm at GMT. I'm at the universal time. And then I go 1 degree west, right? That means I have to take my clock back 4 minutes. Yeah, you'd say that if I went 1 degree west, my time would be 4 minutes behind because I'm 4 minutes behind 0 degrees, right? And you'll learn more of the logic behind that later when you do sundials and things. But for now, that's pretty much it. Using that scale, if you were to do 1 hour, that's 15 degrees. So yeah, which is why we have around like 23 to 24 time zones. Because obviously, if you think 360 degrees and 15 degrees is 1 hour, and we're splitting up every 1 hour, that means that there's 24 times 15 is 360, which means we have 23, like around 24 time zones. So just assess that. I've got a little question here. If it's 4:30 or 16:30 at Greenwich, what time is it at 30 degrees east? So 30 degrees east is here, just so you could like see that. So what time would it be there? So if you guys had a little think about that, you'd find that the answer would be 6:30. Because if it's 30 degrees and 1 degree is 4 minutes, 30 times 4 is 120 minutes. 120 minutes is 2 hours, which means you add 2 hours because it's 2 hours ahead. So 16 plus 2 hours is 6:30. If you had a little trouble with that one, try thinking about maybe where Greenwich is. So when we say Greenwich, we mean prime meridian. And when they ask these questions in exams, they'll try and trip you up a lot like that. So they'll say in London or in Greenwich or on this line, and you just got to try and think that's the prime meridian. That's 0 degrees longitude. Uh, I've kind of already said all this and explained them, but just to recap, these are your important parts in the Earth: Arctic Circle, Tropic of Cancer, Equator, Tropic of Capricorn, and Antarctic Circle. You'll need to know like where exactly these are in terms of latitude, so it's good for you to just note them down. One of the final things we have to cover is the color of the sky. So why the sky is blue. I'm sure a lot of you, again, a lot of you have probably already learned this before, but we just got to cover it again just to like regain our foundations. So when you've got light coming in from the sun, Earth's atmosphere scatters it due to the ozone and everything else inside the atmosphere. So it scatters it so that all the light is spread over instead of just concentrated in one spot. And because blue is the shortest wavelength of visible light, so red is the longest on one end of the spectrum, and blue is the shortest, it gets scattered the most, which is why obviously when you look up, the sky is blue. In this country, it's grey most of the time because of clouds, but if there wasn't clouds, then it'd be blue. That doesn't mean we can't see obviously other colors in the spectrum. See, those aren't the only colors we can see. When you look at sunset, you can see oranges and reds. And the reason for this is because of the angle of the sun in the sky. So I've got this diagram here. If you think when you're looking at the sun, right, it's got a really low angle in the sky, which means obviously as you see here, when it comes towards us, there's a lot more scattering happening because if you think literally, there's a lot more atmosphere for it to pass through. Obviously, in this diagram, the sun's way farther away, um, but the effect is the same. So because there's much more atmosphere there, like for it to go through, a lot more of the blue light is scattered, and because there's less blue light coming, less other colors coming, a lot more of the red light and yellow light of longer wavelengths can come in and enter our eyes, which obviously makes it look red and yellow and orange and all those beautiful colors. So the next thing we have to cover is something called, oh, just loads, light pollution, right? So light pollution is kind of in the name, right? It's light made from humans, man-made sources that like pollutes the sky. So it just blocks the view of the smog. Sometimes it can be like smog from cities, or a lot of the time it can actually just be like light sources. An important thing to note is as well, light pollution is always artificial. When we're talking about pollution specifically, you can have other sources which block your view of stars and other celestial objects, which we call interference, like the moon. So you say the moon is light interference because it's interfering because it's really bright. It's interfering with your view of other stars. But light pollution is man-made only. So examples of light pollution are, you know, street lights, city lights, most lights, car lights, headlights, anything that like has light on it emits light. Anything that is in direct view of your eyes um, creates light pollution. And you can see this scale we use here. Forgot what the name of the scale is, but yeah, so this is called the Bortle dark sky scale, which shows how like higher levels of light pollution you can see less. So if you somehow manage to get to a dark sky park or an area in the sea or any location that had basically no man-made light, no human light, this is what you could see. But then in most cities, in most towns, even in most like counties, even in the rural side, about six is about the least you can see in general, just areas. And when you get to like inner cities like London, Southampton, all those places, 8 to 9. You can only see like the moon. So the whole thing behind why light pollution is a problem is to do with your eyes themselves. So if you think when you have something bright shone in front of you, your eyes constrict to not let as much light in, so that your retinas don't get burned, your eyes don't get damaged. And so the whole point with these observations, observing celestial objects, stars, moon, everything, is that you want to go outside in the dark so that your eyes dilate as much as possible, so that it let in as much natural light as possible. And obviously, if you've got headlights and car lights messing that up, it's not only is it constricting your eyes, right? So that like they get smaller and you can't see as much natural light. It also blocks it because you've got a really bright source of light. And let's say you're looking up, right? Uh, and there's a star behind a street light. you can't see that star because that street light is so bright. It's the only thing you can see, which is why it's a problem when we try to do observations and things in busy areas or somewhere that's not like a park or away from villages or towns and cities. But that's not the only thing. When you have light pollution, it creates this effect here known as sky glow, and you can kind of see this over here in this photo. Sky glow is created when you've got all these dust particles and molecules in the air, and when the man-made light hits them, it sort of like spreads them out and it emits it as well. So actually, another thing I forgot to mention as well is the only sources of light pollution like occurring is not just because of man-made light, although that's a part of it, it's a factor. The other factor is normal pollution, all these dust particles, water droplets, air particles in the air create sky glow. So the reason for that is whenever you get light coming, like hitting those dust particles, it sort of blocks them, and that's why you get this. That's why you get this effect, like that brightens up the sky a lot, because you have all this light colliding with these air particles and molecules and creating this effect here. Which means obviously, if you see in this image, if we had some stars in the background, they'd be a lot more difficult to see because you've got the sky glow going on. Another effect of Earth's atmosphere and the cause of it is twinkling. So obviously you see stars twinkling in the sky, but that's not what these stars actually do. That's because of what happens to the light as they enter Earth's atmosphere. So the definition of twinkling is when a star appears to change brightness from the observer's perspective. And obviously it starts twinkling. So that part is pretty self-explanatory, and it's caused by the different like types of wind and temperatures that light has to pass through the atmosphere in order to reach our eyes, which means the brightness can vary a little bit. Usually, if you had no light pollution, you still have some twinkling, but it's a lot more noticeable when you have light pollution as well, because you've like and normal pollution because you've got all these dust particles and smog particles that just block the light as well, which make it twinkle a lot. And then obviously got a gif here of just twinkling stars. So that's pretty much it for the whole topic. But as for every topic, there's a lot of like questions they're likely to ask you. So I just thought throw up a 6 mark question for this topic. They're not that like it's very rare that you'd get one for this specific topic because it's mostly just basic stuff that you go over. It's mostly just facts. But just in case you do, the only type of question I can really imagine they ask you on this is to plan an observation. So, a question like this, where you have to design a naked eye experiment to determine the position of a meteor shower's radiant. Describe what you would record to find the position of the radiant. Describe how you would analyze your observations to find its position. Now, okay, you guys might not have done meteor showers or anything about radiance or their positions or anything yet. So that's not the part I want you to worry about. The part I want you to worry about is this, a naked eye experiment. So you have to think to yourself, in order to observe a meteor shower, which we know is probably pretty difficult to see like for normal people in cities, you have to think what would you need to do in order to have the best position and the best chances to be able to clearly see the meteor shower? And if you don't want to think about meteor showers because you haven't really done it yet, that's fine. Just think about any stars, any celestial objects that you see in the sky. How could you see them the most clearly? And before you start writing down bullet points of things, what I want you to try and think about is times of day as well. So, what times of the day, or sorry, probably not day, what times of the night would be best to do these sort of experiments? So yeah, just the naked eye part you need to focus on. Don't worry about the analyzing of the observations part yet if you haven't done that. All right. So some of the things you could have talked about were talking about getting away from maybe some city location, getting to a darker location away from street lights and headlights, talking about light pollution a little bit, saying that you'd be able to see clearer without it, obviously, because you can see more. Um, oh, another thing, that technique of what we talked about for wanting to get your eyes to dilate fully, that's called dark adaptation. That's a good piece of key terminology you can put because in at least one of your two papers, I can almost guarantee you'll get a 6 mark question like this where you have to design an experiment. So it's usually a really easy piece of terminology to just throw in there if it's naked eye. Say use dark adaptation way outside in the dark for 20, 30 minutes and just let your eyes dilate so that you can let more light in so you can see more stars. So yeah, that's pretty much it. Topic one, it's not really tough or anything. It's just a bunch of facts, some things you might have already known. Um, no, it's not very long actually, the content itself, but I stretched out a bit. That's my bad. Let me know if there's any questions, and I'll put the resources somewhere.